Hello everyone and welcome to the second part of this two-part video course introducing high-performance computing. It is brought to you by the Belgian National Competence Center in High-Performance Computing, CÉCI Belgium. In the first part, we introduced you to supercomputers and we have shown what they are used for. We also described the evolution of supercomputers and presented those to which we have access today in Belgium. In this second part, the structure of supercomputers will be briefly described, followed by a short explanation of how to interact with them. Finally, we will see how we can benefit from the use of supercomputers using parallel computing, and what are the issues of parallelization. Here we go for part 2. So, what is a supercomputer or a computing cluster, and how does it work? Obviously, you cannot be locally connected to the supercomputer, as it is often in another location. Just as you access your personal data in the cloud, you connect to the supercomputer through a secure network protocol called SSH. So, from your personal computer, you access the login node. This login node is not adapted for large calculations. You have first to write a script describing the computer resources needed. This script is read by a scheduler, like slurm, which then distributes the jobs to the computer nodes. To gather all the results of your calculations, a global storage system, accessible from all computer nodes, is also needed. Optionally, some nodes have also accelerators, usually GPUs, which can be really efficient for some tasks, for example in machine learning. The basic components of the supercomputers are the nodes that act as a single computer. These nodes are stacked in large racks that allow for cooling. Each node is composed of one or a few CPUs, but also some RAM and a little storage. Each CPU is composed of several cores, and each core can work on a different task. A shared cache is also used for the communication between each core. GPUs, or graphic processing units, can be used for high-performance computing and are no longer uniquely used for image processing and video games. Such GPUs, used for general purposes, are called GPGPUs. CPUs and GPUs serve different functions. CPUs are used for sequential but very complex tasks, using, for example, pipelining, which consists of starting a new task when the previous one is not completed. Therefore, CPUs are fast and can operate with a large frequency, around 4 GHz, which corresponds to 4 billion operations per second. On the other hand, GPUs are used for massively parallel computations. Compared to CPUs, which have a few powerful cores, GPUs have lots of less powerful cores. This enables massively parallel computing with high performance on a single device, but requires appropriate programs. In general, GPUs are designed for simple precision. However, for scientific research, double precision is often needed. But now, there are dedicated GPUs for HPC, such as the AMD Instinct or the NVIDIA Ampere. To access a supercomputer, you either need to use the command line on Linux or Mac, or you need some specific software, as MobiXterm, as shown on the right here. First, you connect using an SSH client. Then, you can interact with the supercomputer using a terminal, as shown in the example with Dragon 2, the cluster of the University of Mons. There are also internet portals for connecting to supercomputers, with a graphical interface to simplify the user experience, but these are not yet available with all supercomputers. To submit your jobs, you interact with the scheduler, such as slurm. You must write a script where you indicate the maximum time duration of the task, the number of cores, and the memory needed, as shown on the right. Then, the job scheduler puts you in a queue according to the resources needed and those that are available. If your task exceeds the time or memory limits, then the job is automatically stopped. However, if you ask for too much time or memory, your jobs may stay too long in the queue. Therefore, this resource request must be carefully handled. In Belgium, Tier 2 supercomputers have different purposes. Some have large memories, some can be used with a large number of cores, up to several hundreds, but on a limited time, while others can handle jobs that last several days. So, even before connecting to a supercomputer, be sure to find the one that matches best your needs. We have seen that supercomputers have a large quantity of resources. But how can we use all these resources efficiently? Supercomputing offers some obvious advantages. Jobs that need large amounts of memory, from several tens of gigabytes to terabytes, can be handled. And jobs that would take several days, months, or even years can be done in a few hours. But this larger computing power comes with other issues. Indeed, large amounts of memory are needed, but it is not simple to manage it. Also, to really benefit from the large amount of cores, the user needs to parallelize its code, which is not straightforward. This brings us to the notion of parallel computing. A simple analogy will help you understand how parallelization works. Consider a person building a Lego house. It takes him 2 hours. If he gets help from another person, it will take him maybe a little more than 1 hour. The cores in a supercomputer work in a similar way. Every core is doing a different task in parallel at the same time. But of course, the program must be adapted for that. In the simplest case, the parallelization is done over a loop where each iteration is independent of the others. However, some parts cannot be done in parallel. Within our example, maybe the second builder is to wait for the first builder to put a brick before putting his own Lego brick. Moreover, communication is necessary between the workers, and this communication takes some time. Therefore, the total time for 2 builders will be longer than half the time for 1 builder. When running a program in parallel, the parts that cannot be parallelized, for example reading an input file, limit the speedup. Jobs that can be totally parallelized are called embarrassingly parallel, but in general, it is not the case. Imagine a job that takes 8 hours to complete. If 75% of the time spent is in a part of the code that is parallelizable, so 6 hours, then with 2 cores, the time duration will be 2 plus half of 6 equal 5 hours, which corresponds to a speedup of 1.6. With 3 workers, the time duration will be 4 hours, so a speedup of 2. We observed that the speedup increases much more slowly than the number of cores, and that we are always limited by the serial part. From Amdahl's law, we can calculate the total maximum speedup of a code, knowing the proportion of the parallel part and the number of processors. Of course, this doesn't take into account the communication between the cores. The effective speedup will always be smaller than this limit. Applying this formula to different parallel parts, we observe that even for a parallel part of 95%, the maximum speedup of 20 is nearly reached around 100 cores, and it is counterproductive to ask for more cores. This shows the importance of knowing which part of the job runs in parallel. To use Tier 1 and Tier 0 supercomputers, where you can ask for thousands of cores, it is clear that nearly 100% of the calculation must be parallelizable. The way of doing parallel computing we've just explained involves what is called strong scaling. In this case, a given problem is divided into smaller and smaller tasks when increasing the number of cores, but the total size of the problem is always the same. Here, a square represents the time spent by 1 core to solve one task. However, there is another way to do parallel computing, the weak scaling. In the weak scaling case, the problem is small in the beginning and a new core is given a similar problem. So, the number of cores increases when the number of tasks to be solved, and, in theory, if you assign one task to one core, the calculation time should be the same, whatever the total size of the problem. This weak scaling is much more efficient than the strong scaling. Let's repeat the advantage of this case. Your program solves the problem with one core. Then, if you increase the size of the problem by a factor n and the number of cores by the same factor n, then the calculation time will be the same as for your initial problem. This also means that the speedup increases linearly with the number of cores, whatever the size of the non-parallelizable part. This is known as Gustafson's law. However, as for the strong scaling case, this is the ideal scenario, where communications are not taken into account. There exist different models to perform parallel computing. The two main models are the shared memory model and the distributed memory model. These models inevitably induce some overhead. In the shared memory model, all the workers use the same pool of data and share the same memory. The drawback is that you need synchronization between the workers. In the analogy with Legos, the builders work with the same pieces, but must talk to each other to be sure they do not interfere with what the other is doing. In the distributed memory model, the workers are completely independent. Each one has a separate set of data and a different memory on separate nodes. Consequently, they need to communicate at the end to gather all the data. In our Legos analogy, each builder is building a totally different part of the house, but in the end, they need to share their work with each other to have a full house. Compared to shared memory, which could be performed on the same node on different cores, and therefore also on a single computer, distributed memory necessarily needs a full cluster with several nodes. In general, both can be mixed to allow for more parallelism. In the end, the main problem is that each worker, each core, must have the same amount of work to be done, such that no workers must wait for the others. This load balancing is quite critical to perform efficient parallel computing. The hierarchy between the different types of storage is also critical. If a core needs information from the RAM, this will take more time than if this information is in the cache. In general, the further away from the core, the slowest. In practice, each core keeps the most important data in some registry, which are written from local caches at a core level L1 or L2. The synchronization between the local caches must be done through another cache command to the CPU, here L3. If the information is not in the cache, the cores need to access the RAM, and this will slow the calculation. And it's even worse if the information is on a disk or on another node. In consequence, the information must be as close to the core as possible, and this shows that communication is a bottleneck for distributed memory models. For GPUs, the RAM is even different than the RAM of CPUs, so the information must also be transferred to the GPU efficiently. In practice, how does the user make a program work in parallel? There are several methods that depend on the level of parallelization. At the core level, there is the principle of vectorization, which consists of performing several similar operations all at once as a vector operation. Then, at the node level, we have the shared memory parallelism with multi-threading and the OpenMP API. OpenMP offers a simple way to do parallel computing and has been adopted by a wide part of the scientific community. It runs on macOS, Windows, and Linux. Its implementation is quite simple and possible with programs in Fortran, C, or C++. For GPUs, there exist different protocols depending on the type of graphic card. CUDA is for NVIDIA, HIP is for AMD, and OpenMP is also a protocol for accelerators. Finally, at the cluster level, MPI, for Message Passing Interface, is the most used standard for distributed memory. MPI has been implemented in lots of programming languages such as C, Python, Fortran, Perl, Java, and so on. But its implementation in a program is more complicated than OpenMP. There also exists an open source version of MPI called OpenMPI. You should also know that there are several libraries that can perform lots of standard mathematical or numerical operations. For example, for algebra, you have the libraries BLAS and LAPACK. For the fast Fourier transform, there is the FFTW library. For writing and reading files in parallel, you can use HDF5 and netcdf. Maybe all of this looks complicated to you, and you don't want to spend too much time learning how to program in parallel. However, there is good news for you. A lot of scientific programs already have parallel versions and are already installed on the clusters. All you will have to do is to check that you use the correct amount of nodes and cores such that the clusters are used efficiently. But this doesn't need much more than a few basic computer skills. So, it's the end of this course on HPC. Let's draw now some conclusions. We have seen that the method that enables the incredible efficiency of supercomputers is the parallelization of large-scale calculations. This parallelization can be done using different methods on a single node, on several nodes, or on GPUs. All these methods have their advantages and their drawbacks. The main disadvantage stands in the necessary communication between the different processing units, and this must be carefully handled. But the important message that you should remember here is that you don't need high programming skills to use supercomputers. Their use is simplified to reach as many researchers as possible. Of course, for those who seek challenges in computer science, the demand for people who program on HPC systems is quite high, so don't hesitate to learn these programming models. If you need more information about HPC and supercomputers in Belgium, if you want video training or information about future on-site training, you can find them on our website or on the website of the CÉCI and of the VSC. And of course, you can contact us using our contact form on the website. Finally, we would like to thank our funders, the European Union, the FWO and the Walloon regions, and our partners, Senairo, the VSC and the CÉCI. We would also like to thank you for watching the video, and we hope you will be joining the HPC community very soon.